Greetings, students. Mr. Keister here again with you today. Today we're going to do Lab 12.1, study of the kinetics of reaction. In our last couple lessons, we've been talking about kinetics and reaction rates. And in our last lesson, we talked about rate laws. In this particular lab, we are going to determine the reaction orders and the rate law of a particular reaction. As I look behind me, had we been in school, this would have been happening on April 24th. Had we been in school, that's for Chem 2. If you're in honors, it would have been a few days after that. But as I've said many times before, those do nows are out the window, and we are now using our modified calendar and do nows document that's located on my Canvas homepage. So, without further ado, let me unfreeze the screen here, and we will look at our lab. So in this experiment, we'll study the kinetics of a chemical reaction. This reaction is called a clock reaction because of the means of observing the reaction rate. I think I mentioned this before in class, but the very first day of school back in August, we did a lab that actually involved reaction rates, and that was a clock reaction also. If you recall, we had two solutions, A and B, that were both either a little bit cloudy or mostly clear, and we poured them together, A and B, and then measured the time it took for the reaction to occur. And we were able to tell that because the color of the solutions when mixed together changed from, like I said, a clearish, cloudyish looking to a very dark purplish brown color. And that signified the end of the reaction. And so, and there was iodine located within the contents of that reaction as well. And iodine serves as the clock, as it will in this one too. So the reaction involves the iodination of acetone. So this is acetone, C3H6O. That is a common name that is used a lot. The actual correct name, organic name, is propanone, which is our smallest ketone. And so our reactants are acetone or propanone and iodine. And also we have a third reactant is actually HCl, which is the source of hydrogen ions that you see here. This reaction has to occur in acidic solution in order for it to happen. And so actually the hydrogen ion, which comes from the HCl, is also a reactant, and it is part of the rate law. This is the net ionic equation for that reaction. So our rate law is this: rate equals K, the rate constant, times the concentration of acetone raised to some power, concentration of iodine raised to some power, and the concentration of hydrogen ion, which again comes from HCl, raised to some power. And those powers are, of course, the reaction orders for each of those three reactants. And we're going to measure each of those in the lab today. So the procedure is here. We're going to come to back to that in a few minutes. I want to go ahead and advance this up to the data table page. Okay. So this will give you a general idea of what we're doing today. We're going to run 5 separate experiments. And as you can see, here are our 3 reactants: 4 molar acetone, 1 molar HCl, 0.0050 molar iodine. And we have a 4th reactant here, water, which is not part of the rate law, but acts as a volume equalizer. And I'll explain that shortly. As you can see in experiment 1, we're going to take 5 mLs of acetone, 5 mLs of HCl, and 5 mLs of iodine. And to those 3, we're going to also add 10 mLs of water. If you add those up, we get 25 mLs total. In the second experiment, we are going to change the amount of acetone that we use. We're going up to 10 mLs. We're leaving these 2 the same. That should send off a bell in your mind, say, oh, I see now. Remember, when you're determining a reaction order for a particular reactant, you must keep the concentrations of the other reactants constant so that you can see that the change in the rate is due solely to the change in concentration of the one reactant that you're changing. As you can see here, between reactions 1 and 2, that's exactly what we've done with acetone. We're changing the amount of acetone while keeping the other two reactants constant. So anyway, 10 mLs acetone, 5 HCl, 5 iodine. Now that totals 20 mLs. And so this time we're only going to add 5 mLs of water, which gets us to that same volume total of 25 mLs. We've done the same thing in reactions 3 and 4. We have varied the concentrations of one of the reactants while keeping the other two the same. I should say varied the volumes of the two one of the reactants while keeping the other two volumes the same, and then use the appropriate amount of water to have the total volume be the same for all the experiments, which is 25 mLs. Reaction 5, same thing, 7.5 of each, only 2.5 mLs of water there to give us again our total of 25. So these are the volumes that we will measure out of each of the reactants for each of our experiments. Now, in data table 2, which is the important one, it talks about adjusted concentrations, all right? Adjusted concentrations. Here is why that says that, all right? So I already have some numbers written in here, and I want to explain where those come from. So let's look at this. So here we have 5 mLs of acetone, and that is just acetone, all right? There's acetone particles in there and nothing else. But when we add in the HCl, the iodine, and the water, the number of acetone particles remains the same, but the volume of the entire solution has gone up, all right? Which means that the concentration of the acetone has been diluted, all right? So think about that. Here's 5 mLs of acetone, it's all acetone, but now we got 25 mLs volume total, but still of that 25 mLs, only 5 mLs of it is acetone. And when you take 25 divided by 5, you get 5. We have diluted, excuse me, my eye's itching there. When we add the rest of our ingredients here, we have diluted the volume of acetone from 5 mLs to 25 mLs. So this is where the adjusted concentration comes in. All volumes that initially started at 5 mLs and ultimately ended up at 25 are being diluted by a factor of 5. And so right here, dilution factors for all 5 mLs will be diluted by a factor of 5. So now let's run down here and see how we use that. So our actual concentration of acetone was 4 molar. But that was with 5 mLs. When we diluted it to 25, if you take 4.0 molar and divide that by 5, you get a diluted concentration of 0.80 molar for that acetone. Same here with number 3. This was 5 mLs. That would be divided by 5 as well. So this one would also be 0.80 molar. And 5 mLs here, same thing. The 4 molar original divided by 5, 0.80 molar. And I can do that on the other two columns as well. Here it's already done for us here. So HCl started out at 1.0 molar, but when we go from 5 mLs to 25 total and divide that by a factor of 5, 1.0 divided by 5 gives us an adjusted concentration of 0.20 molar. And so as I look here in number 2, we also started with 5 mLs. So that would be also 0.20 molar, and that's it for that column. When we get to the iodine, iodine initially was 0.0050 molar. Again, we start with 5 mLs and dilute the whole thing to 25. We're again diluting by a factor of 5. So if you take 0.0050 and divide that by 5, we get the adjusted concentration of 0.0010 molar. We're going to do the same thing for the next two because it's the same initial volume and diluted by the same factor of 5. So those would also be 0.0010 mole. Now, here we have some tens, all right? So if you start out with 10 mLs initially at 4 molar, but we end up with a total volume of 25, now 25 divided by 10 is 2.5. So we have diluted now our original concentration by a factor of 2.5, and that will be true then of all of the initial concentrations that we ended up starting with 10 mLs and then diluting to the total of 25. So this one here, we would take our original concentration now and divide it by 2.5, which then gives us 1.6 molar here. These are all 2 sig figs, by the way, based on our concentration. Which makes sense. This is double this because we diluted this by half as much as we did the 5 ml ones. These two are also both 10, so we would take our 1.0 molar and divide by 2.5 for both of these. And so these then come out to be 0.40 molar. And then we have 110 over here in the iodine. And so that original concentration of 0.50 molar divided by 2.5 gives us 0.0020 molar. Okay. Again, water, we don't really care. Water is just the substance that brings the volumes equal for all the solutions, which is necessary to do. The last one, number 5, we have 7.5 mLs originally of actually all 3 of these. And if you take 25 divided by 7.5, you get 3.3 repeating. So our dilution factor for all the 7.5 ml ones is 3.3 repeating. So if we take the original concentration of acetone, 4.0, divided by 3.3 repeating, gives us an adjusted concentration of 1.2 molar. We take our 1.0 molar HCl and divide it by 3.3 repeating, the dilution factor. We get 0.30 molar. And then if we take our original concentration of iodine, 0.0050, divide that by 3.3 repeating, gives us an adjusted concentration of 0.0015 molar. Okay? Why did we need to do that? Because with determining a reaction order, all right, we use concentrations. We don't use volumes. All right? We use concentrations in determining reaction order. So it is necessary not only to use concentration rather than volume, but make sure we're using the correct concentration. Because like I said, even though this was 4 molar initially, that's just when you have acetone by itself. When you add all the other stuff to it, the amount of acetone is still the same, but the volume has gone up, which is going to cause your molarity to go down. Okay? All right, so this takes care of this portion. We're going to go back here in a second and talk about the procedure itself, and then we will come back and fill in the rest and then take a look at the calculations. Okay?